Welcome to The Explainer. Today, we're diving into one of the most fascinating little glitches in how we understand everyday physics. We're taught from a very young age that light travels in a perfectly straight line. But what happens when that light hits a microscopic obstacle or squeezes through a tiny gap? Well, it doesn't just cast a sharp shadow. It flares out. It bends. It creates these incredibly intricate, glowing patterns. Today, we're exploring exactly how light breaks its own intuitive rules. We are decoding diffraction. Listen to this. It's basically the source code of the universe. When waves encounter an edge, an obstacle, or an aperture, those waves spread out as they travel and, as a result, undergo interference. This is called diffraction. This flaring out, this rippling spread, it's the underlying mechanism for so much of the technology and natural phenomena all around us. Here is our roadmap for today's explainer. We're going to cover 1. Bending the rules of light. 2. Calculating the diffraction intensity. 3. Circular apertures and visual limits. 4. Double-slit diffraction dynamics. 5. Gratings, dispersion and resolution. And finally, 6. Seeing atoms with X-rays. Let's jump right in. Section 1. Bending the rules of light. So let's kick things off with a fundamental question. What exactly happens when a wave of monochromatic light hits a single microscopic slit? It doesn't just paint one straight line of light on the wall behind it. Instead, it flares out into a broad, central band, which is flanked by alternating dark and bright fringes. Okay, let's dive into this. There's an incredibly elegant formula for this. A sine theta equals m lambda. This equation dictates exactly where the light waves perfectly cancel each other out to create total darkness, what we call the dark fringes, or minima. Here, A is our slit width, theta is the angle from the center, lambda is our wavelength, and m is just an integer, the order number, like 1, 2, or 3. If you imagine dividing a tiny slit into imaginary zones, wavelets from the top zone perfectly match up with wavelets from the bottom zone, completely out of phase. They essentially destroy each other at these very specific angles. Section 2, calculating the diffraction intensity. Right, so we know exactly where the light vanishes into those dark fringes. But what about the brightness between the dark spots? How do we measure the actual glowing intensity of the light as it spreads? This is where it gets incredibly cool. We calculate the intensity at any angle theta using the formula you see here. To really picture it, imagine tiny, glowing, rotating vectors called phasors. Each wavelet passing through the slit is one of these phasors. When you look right at the dead center of the pattern, all those glowing arrows line up perfectly straight, giving you the absolute maximum intensity. But as you look off to the side, at an angle, those vectors start to rotate and literally curl into an arc. The tighter that arc curls, the shorter the total resultant vector becomes, and the dimmer the light gets, perfectly matching that sine alpha over alpha squared equation. It's an absolutely beautiful geometric dance, determining exactly how bright the light is at any given point. Section 3, Circular Apertures and Visual Limits. We've been talking about narrow, rectangular slits so far, but let's ask a crucial what-if question. What if the aperture isn't a rectangle at all, but a perfect circle? Like a telescope lens, or even the pupil of your own eye. Check out this mesmerizing bullseye pattern. When light passes through a circular aperture, it doesn't form straight bands. That bright, glowing maximum right in the center is called the airy disk, and the math shifts just a tiny bit here to account for this circular geometry. The first dark ring, the edge of that bullseye, is located by the formula sine theta equals 1.22 lambda divided by d, where d is the diameter of the circle. That little 1.22, that is a geometric constant that fundamentally limits literally everything we can see in the universe. And this brilliantly illustrates exactly why that circular diffraction matters so much. Imagine two light sources, maybe two stars or cars' headlights way off in the distance. When they're just barely resolvable as two distinct points versus when they've completely blended into a single blurry blob. That is Rayleigh's criterion. It states that two objects are on the absolute verge of being resolved if the central airy disk of one sits exactly on the first dark minimum of the other. This one simple rule dictates whether a multi-billion-dollar spy satellite can actually read a license plate from space or if it just sees a meaningless smudge. It all comes down to the diameter of the aperture versus the wavelength of the light. Section 4, Double-slit diffraction dynamics. Let's escalate this simulation. What happens if we don't just have one slit, but two of them placed side by side? When you have two slits, you're actually mashing together two entirely different wave phenomena into one intimate interaction. There are two distinct factors at play. The overall broad, hill-like shape of the light pattern, which we call the envelope, is determined entirely by the diffraction factor of a single slit, that sine alpha over alpha squared we talked about earlier. But tucked inside that broad, glowing envelope are incredibly sharp, rapidly alternating bright and dark lines. Those are generated by the interference factor, the cosine squared beta, which represents the waves from the two separate slits colliding. So the diffraction envelope dictates the broad peaks, while interference dictates the sharp internal fringes. They just work in perfect concert. Section 5. Gratings, Dispersion and Resolution. Okay, let's step up the complexity one more time. Two slits give us a really sharp pattern. But what if we multiply those two slits into thousands of slits per millimeter? Welcome to the realm of the diffraction grating, which is essentially a tool of extreme scientific precision. Here's how it evolves, step by step. Step 1, we carve thousands of microscopic rulings onto a surface. Step 2, because we have so many sources of light interfering all at once, the bright fringes don't just get a little sharper, they become incredibly narrow, super intense lines. Step 3, because the angle of these sharp lines depends heavily on the wavelength, different colors of light are thrown out at completely different angles. We call this separation, dispersion. We are quite literally slicing white light wide open to look at its genetic makeup. Now, to ground all this heavy math in reality, just think about a standard compact disc. You've seen those brilliant rainbow lanes that flare across the surface of a CD when light hits it, right? Well, that is not pigment. That's structural color. The disc has incredibly fine rulings, tiny grooves just 0.5 micrometers wide, curving around it. Those microscopic tracks act exactly like the idealized diffraction grating we just discussed, forcing the white light of the room to separate into its constituent wavelengths right before your very eyes. So the crucial point is understanding how scientists actually evaluate these gratings in a lab. We rely on two main metrics. First is dispersion, or D. This is simply how widely the grating spreads apart different wavelengths. If you have two slightly different shades of red, a high dispersion throws them really far apart physically. Second is resolving power, or R. This is the grating's ability to make those lines sharp enough that they don't just blur together into a mess. Notice the formula for resolving power. R equals N times M. N is the total number of slits, meaning if you want to boost your resolution and see finer detail, you literally just pack in thousands and thousands more microscopic slits. Which brings us to a pretty massive what if. We know light bends around physical grooves on a CD, but what if the slits or obstacles in our grating aren't carved by a machine? What if they are naturally occurring planes of atoms, spaced just fractions of a nanometer apart? Section 6. Seeing atoms with X-rays. Now, visible light is just too big to care about individual atoms. Its wavelength simply washes right over them. But if we switch our toolkit to X-rays, whose tiny wavelengths are about 1 angstrom, that's 10 to the negative 10 meters, well, they perfectly match the incredibly tight spacing of atomic crystal planes. And this unlocks the ultimate structural key, Bragg's law, 2D sine theta equals m lambda. By firing X-rays at a crystal, like a tiny grain of table salt, the waves scatter off the different planes of atoms. Because those planes are stacked at a very specific distance, d, the X-rays bouncing off the deeper planes have to travel slightly further than the ones bouncing off the top plane. When that extra distance exactly matches a multiple of the X-ray's wavelength, the waves constructively interfere, boom, creating a bright spot on a detector. By mapping out these spots, scientists literally reverse-engineered the three-dimensional atomic holograms of solid matter. It is exactly how we figured out the double helix shape of DNA. So what does this all mean? We've scaled all the way from a simple slit in a piece of cardboard to the glowing arc of phasers, to the grooves of a CD, and finally down to the atomic lattice of a crystal. I really want to leave you pondering this profound physical boundary, the absolute limits of human observation. Whether you're looking up at a distant binary star system or zooming all the way in on the atoms that make up our own bodies, they depend entirely on the interference of waves and the width of the aperture we look through. Light doesn't just passively travel, it interacts, it bends, and it calculates. The next time you see a beam of light pass through a small opening, I hope you remember the complex, beautiful code of diffraction working right in front of your eyes. Keep exploring, and I'll catch you in the next explainer.